This is unit 2.3 when we are talking about magnetic field. So magnets. Magnets have a north pole and the south pole. The north pole is in the north and the south pole, you get the point. So the north pole and the south pole. Now, the magnetic field of a magnet always goes like this, from the north to the south. What does that mean? Well, we don't know yet, and we don't really need to know in this unit. But what we are going to know that the only thing, not only magnets have a magnetic field, but a wire carrying a current can also have a magnetic field. So current running through a wire. Imagine this is a wire, right? Just a line, and the current is traveling this way. This is the direction of the current traveling from down to up. How do we know which direction the current, the magnetic field caused by the current is going? We know that it's a circle like this, but this circle could be clockwise or anti-clockwise. Now, this involves the right hand rule. The right hand rule is basically when you put out your right hand. Now, this is really important because I used my left hand once and that didn't go too well. So you use the right hand, you curl it up. So you're basically giving someone a thumb up. So now after you have your hand in that position, your thumb should be sticking up and the rest of your fingers should be curled up. Now imagine your thumb is the wire carrying current, and the rest of your fingers are the magnetic field lines. So when I compare my right hand to this diagram, I can feel the missing parts. I can see my fingers curling around my thumb, so we know that the current is going this way. My fingers are coming from here and to here. So that should be where my the end of my index finger is, and imagine that as my hand, like this, right? And your thumb is somewhere over here. So the direction of the magnetic field is like this, going here, and the arrow is like that when it's over there. Now, magnetic field have different concentrations. We usually draw it like this. The closer to the wire it is, more the distance between the halos are shorter. But when it gets further apart, the circles are going to be larger and far more separated from the inner ones. Now, a current carrying wire can also be represented from above it. So now I'm drawing the end of a wire. We're looking at the end of a wire. Just a circle, that's what you see if the wire is straight, right? And now I'm drawing a dot in the middle. This means that the wire is coming, no, the direction of the current is coming towards us. Imagine it coming out of the screen. Now, on the opposite, I could draw an arrow, and this would mean that the direction of the current is going into the screen. Imagine the current originating from you and going into the screen through this wire. But in this case, let's use our right hand rule. Since the direction of the current is out of the screen, you should be giving yourself a thumb up, except pointing your own thumb at yourself, and like, yeah, you should see the top of your thumb and the rest of your fingers curled up. So you should draw something like this. Whoops, that's terrible. The directions should be like this: 1, 2, and 3. Usually we draw a minimum of three circles around, but this is not a circle. This is a front egg or something. But you get the idea. It's meant to be three circles around this wire. And if you did it properly, what the arrows should be looking like is this, going up and then down. That direction. And now if you change the direction of the current, you just flip the arrows. But most of the times we just use the right hand rule to confirm because it's easy. Why not? Okay. Now, since we have learned about um, the direction of magnetic field around a single wire, the more advanced ones are magnetic field produced by a loop of wire. So a loop of wire is going to look something like um, here. Boom, boom, boom. That is a loop of wire. Still one single strand of wire, but it's formed in like a loop. Now, if we do the same thing again, we use the right hand rule, except this time we're going to choose a specific point. So imagine that our thumb is the wire at this part of the loop. You're going to draw something that looks something like this. So the wire, the magnetic field goes up when it's on the inside and down when it's on the outside. And I'm only drawing one, but you should be drawing three, but I have enough space over here. And when you're on the left side, because the current is traveling into the screen like this and out of the loop like that, it's going around the loop and out. So your thumb, when you're trying to draw the magnetic field for this part of the wire, the thumb should be should be parallel to this arrow, right? Should be parallel to this arrow. And you should be drawing um, arrows that come up on the inner part of the loop and come down on the outer part of the loop. And when you see something kind of overlaps that, we see that the arrows on the inner of the loop are both going up and the arrows on the outer part of the loop are both going down. Now the inside looks something like this. You basically draw a few lines like this, boom, and boom. And the lines are all pointing upwards like that, forming a pretty interesting magnetic field. You have little ones on the edge and like a big one in the middle, just going straight through the loop. So this is magnetic field for a loop, and we can also have coil. Now the coils are usually represented like by small circles uh, like this. 1, 2, 3, 4. 1, 2. Oh, this is terrible. 3, 4, 5, and 6. Now, let's say the circles on the bottom are they're not meant to be. You can't see them as circles. You're meant to see them as wire coming towards or away from you. Now, this is gonna be hard. All right. So these are meant to be x's. They're meant to be going away from you, and the current on the bottom are coming toward you because circle and crosses. So what you're going to do is curl your right hand into a thumb up, and then do the right hand rule with individual ones. So you're going to test with the one on top, and you're going to face your thumb into the screen because it's going away from you. It's going into the screen, right? And the magnetic field around this single wire is going to be going up like here and down like on the right. And when you do them, when you see this pattern, if you do this to them all and they are connected, you're going to see this pattern, right? It's a large loop around all of these wires going into the screen, and it's going to be like this. Now, same thing on the bottom here. The wires collectively are going to have this huge magnetic field around them, and the lines are going to the magnetic field is going to be traveling, not traveling, is going to be pointing like this way. Now another thing, the same thing happens. We see that the lines, the direction of the magnetic field in the middle are in the same direction. So we do the same thing here. We draw a few lines in the middle. 1, 2, 3. Oof. And they are in the same direction as these ones on the inside. So we call this structure a solenoid, and really it's just loops of coils of wire. It looks something like this in 3D. Oh my days, that's terrible. One says coils and loops of wire. That's a solenoid. Now this is just a different way of representing a solenoid. But yeah, this is basically the magnetic field around solenoid, and that is unit 2.3. Short, easy, simple.